In class, we're going to discover that when we drive one of our systems with a sinusoidal input, that we receive also a sinusoidal output in steady state. And this is something that you've also explored in the second lab. So one of the interesting things to characterize then is the magnitude of that sinusoidal output and the frequency of the sinusoidal output. And so these characterize completely the response if the response is a single sinusoid. And so the Bode plot, which is the topic of this video, is a specific way of plotting these magnitudes and phases over different frequency ranges. And so again, the transfer function g provides the response of the system. And if we evaluate that only at oscillatory inputs, I omega, that we can then observe what happens in the output. And what we're going to do is we're going to divide that into the magnitude part and this exponential, which is essentially driven by the angle of that complex value g of I omega. All right, and so again, the magnitude is simply just given here. It's the real part of that squared plus the imaginary part of that squared, because g of I omega is a complex value. And then the angle or phase of g of I omega is just given by the inverse tangent of the imaginary part over the real part. And so we're going to use the atan2 argument version of that, which provides you with the correct quadrant when you take the inverse tangent. So the Bode plots are fairly standard. They'd essentially be exactly what you would do if you tried to make a plot about this. The only special part is, so there's three things. It's the fact that the magnitude is on a log-log plot, which means that you take the log of the horizontal axis, the frequency, and a log of the magnitude of g of I omega. And the phase is on a semi-log plot, which means that we take the log of the frequency on the horizontal axis and we keep the phase in angles. So we're going to keep that in degrees just so that we can read it nice and easy. The reason why we change the magnitude is because the magnitude changes quite dramatically. And so it's useful to characterize it on a log plot where those dramatic changes can be seen without kind of squashing the rest of the information. The last piece is the fact that this magnitude is actually expressed in decibels, and this is really just due to history. A lot of Bode plots were originally used on telephone systems and auditory systems, and so they were really interested in understanding essentially how loud the sound was that was gonna come out. And so oftentimes this came from this notion of decibels. Plotting in decibels comes from that. And there's actually some more history about this 20 that has to do with topics in electrical engineering and circuitry. But it's conventional then to plot, instead of just the magnitude of g of I omega, we actually plot the magnitude of that evaluated in decibels. And so if we evaluate the log 10 of g of I omega, so that just means a base 10 log, then we multiply that by 20, and that provides us with the decibel version of that magnitude. And remember, the magnitude of g of I omega is simply just the magnitude of the output divided by the input. So it's the ratio of how big the magnitude of the output is compared to how much the signal that we're injecting. And so one of the really cool things about Bode plots is that we can combine them and build them in modular pieces and then combine them together. So if we have this kind of arbitrary system up here that has 2 zeros and 3 poles, that when we evaluate g at I omega, then we plug in I omega for s, and we get each of these expressions. And each of these parenthetical expressions will result in general, a complex number, because we have this I omega, and then we have z1, z2, p1, p2, and p3, which could be complex valued. And if we decide to go ahead and convert each one of these into polar form, then each one of them has a magnitude and has a phase. And we can do that for each of the 5 different elements. And if we had more elements, then we could continue doing this. And so each one gets a magnitude and a phase. And so once we put this in polar form, it's actually easy to factor this out. All of the magnitudes can be combined together into a single term. And then you can combine all of these exponentials in a single term. And notice what happens is the phases of the zeros, because they're in the numerator, they keep their positive sign. But the phases of the poles down here, these 5 variables, these enter with a minus sign because they appear in the denominator. And so when we bring them into this exponential, they subtract. And so this represents the phase of this entire, remember this whole thing is a complex value. And so this represents the magnitude, and then this represents the phase. And the cool part here is the fact then that the magnitudes, we can express the magnitudes all together and we express the phases all together. And if we take the log of the magnitudes in particular, then using the multiplication and division rules of the log, this actually reduces to the log of the first 0 plus the log of the second 0 minus, because the pole is down here in the denominator, minus the log of the first pole, minus the log of the second pole, minus the log of the third pole. And again, these quantities are of P1. These are the magnitudes of each of these elements, each of these pieces here, which correspond to each of these terms. So the outcome here that we observe is that when we take the log of the magnitude, this allows us just to take the sum or difference of essentially those zeros come in with positive sign, the poles come in with minus sign, and the resulting log magnitude is given just by this sum or difference of all of the individual magnitudes of the poles and zeros. In the same way, if we just look at the angle that we've defined here, the angle is just given by, again, the sum from the zeros, the 0 angles, and then subtracting off the pole angles. And so if we just simply sum log magnitudes and sum phases of each of these components, then we can aggregate the complete Bode plot. So the complete Bode plot of g of I omega is given by essentially the sum of the individual Bode plots for the first 0, the second 0, the first pole, and so on. And so if we just sum these together, this actually gives us a very easy way of composing the complete Bode plot. To give you a concrete idea of what it means to evaluate g of s at the value I omega, if g of s is simply the very simple transfer function s, then we plug in I omega for s, and that means s becomes I omega. And now what we're interested in doing is evaluating the magnitude of that and the phase of that. So the magnitude is simply just, so remember this is equal to 0, real part, plus I omega. And so this is simply just 0 squared plus omega squared square rooted. And that gives us the magnitude of just omega. And if we take the base 10 log of that, then that just becomes the base 10 log of omega. And if we put that then in decibels, we just multiply by 20. So just multiply the log 10 by 20. And so this is the value of our magnitude for our Bode plot on a log system. And so if we calculate the phase, then the phase is the inverse tangent of the imaginary part and the real part here. And the real part 0, so that automatically makes the arctangent at plus 90. And so the plots of this, essentially this frequency domain is given in log terms, and so that's why we're incrementing in equal intervals, essentially this interval from 0 to 0.1 is the same length as 0.1 to 1, and these are factors of 10. So each time I move from here to here, from here to here, there's a factor of 10, and so that's what makes it a logarithmic scale. And on this logarithmic scale, we evaluate the decibel magnitude here, and that means that I take the log of that essentially this decibel is linear in the log of omega. So that means that it looks linear on this log plot. And then the angle is simply just given at plus 90. So to see a similar example, we can use this simple transfer function 1 over s and evaluate the real and imaginary parts of g of I omega. So if we plug in I omega for s, then we get 1 over I omega, and then we can use our complex valued rules to multiply top and bottom by I, and that gives us this minus sign because we get essentially this, the in-between step is that we get I over I squared times omega, and so this becomes minus 1. And so if we evaluate the magnitude and phase of this, again, this looks like 0 squared plus 1 over omega times squared, or square rooted, and that gives us this magnitude. Again, taking the log of that means that we get the log of 1 over omega, and we can use the log rules to take down this exponent and get the minus out front. So we get minus log of omega. And putting that again into decibel, we multiply by a factor of 20. Again, we look at the phase, and the phase, even though this value has changed, it's now minus, which gives us a minus sign out front, but there's still 0 really real part, so that leaves us still at 90 degrees. And so now what we get when we plot these Bode plots is we get the exact same thing with a different, essentially opposite slope, so the negative slope, so it's going in this direction instead of this direction, and we get a minus 90 phase. In class, we'll see several examples of how we build out the rest of our building blocks for transfer functions, and then we'll see how we can combine them together in order to get the complete Bode plots for complex transfer functions.